some questions for you, Aaron Crow, is it?
What am I doing? What am I even doing in here? I didn't even do anything.
I asked the questions here.
Fine.
First question. What does this mean?
Alright, so for this one, all you do is you plug in 0 for each of the t's. So it would be 0 cubed minus 8 times 0 squared plus 15 times 0 plus 5. Now, anything times 0 is 0. So all you're left with is this 5. And so when t is 0, it equals to 5. Which makes sense because t is the equivalent of the x. And so when x is 0, that dot is about 5. And then the next one, when t is 5, you do the same exact thing. And I just put it into the calculator right here. And so it's 5 cubed minus 8 times 5 squared plus 16 times 5 plus 5. And that all equals 10. So when t is equal to 5, then the y is 10, which also matches up to what it looks like on the graph. So this just means after 0 hours, you are at your starting point, which for us is the school, which is 5 miles away from your house. And then after 5 hours, you're 10 miles away from your house. And also, and then for your maximum and minimum distances, you can just look on the graph and see the highest point, which here is around 14-ish miles. And then for the minimum distance, it's just the bottommost little curvy thingy, and here it's about 5 miles. So maximum and minimum are pretty easy.
Interesting. What are the intervals then?
Well, it looks like for the intervals, when you're moving towards your home, it's about 1.3 to 4, and we're moving away from your house, it's 0, 1.3, and then 4 to 5, because 5 is just where the graph ends.
How do you know that?
Because the y-axis is the distance in miles, so when y equals 0, you're at home. Meaning when the graph is going towards 0, you're moving towards home, and when the graph has a positive slope, or moving away from 0, or moving away from home as the y value increases.
Okay, so how do you find the velocity in question 2?
You just find the derivative of the first function.
How do you find the derivative you speak of?
For this one, it looks like it can use the power and the constant rules.
How does that work?
The first thing I like to do when I'm finding the derivative is to rewrite the equation, because this is just the original equation, which is right here. I just rewrote it down here just to make it easier. And the first rule to do is to find the derivative of this function is to use the power rule. And the power rule is when you take the derivative of a constant with an exponent, it is equal to taking that exponent and multiplying it, and then subtracting that exponent by 1. So for this, it would be 3 times t squared, because 3 minus 1 is just 2. And then you just do the same for each one. So it'll be minus then this would be 8 times 2t plus 16 times t, well, times 1 t to the 0, and then plus 5. And t to the 0 is 1, and it's just 1 times 1, so I can just get rid of that. And then that would all equal 3t squared minus 8 times 2 is 16t plus 16. And then for this 5, it's the constant rule. And whenever you take a derivative of a regular number like this that doesn't have any letters or any specialty to them, it just equals 0. So this would be the derivative of this original function. So the derivative s of t is equal to 3t squared minus 16t plus 16.
Can you graph this function?
Of course, just throw it into Desmos.
That's actually pretty cool. Now, what happens if it's 1 or 3?
Oh. For 1 and 3, you just do the same exact thing as you did last time, where you just plug in 1 for t. And then that will give you 3, 1 squared minus 16, 1 plus 16. And that all equals 3. So then v of 1 equals 3. And you do the same thing for 3. So it's 3 times 3 squared minus 16 times 3 squared plus 16. And that all equals 5. And you can just plug these into the calculator and it'll spit out the problem. And this is actually -5. Sorry. And these just mean that after an hour, your velocity will be 3 miles per hour. And then after 3 hours, your velocity will be -5 miles per hour. And in this case, when it's positive, you're moving away from your house. You're moving 3 miles per hour away from your house. And then for this, it is -5. So you're moving towards your house. So this would be -5 miles per hour towards your house.
So velocity can be a negative?
Of course. The negative just means that you're moving towards your house, and it's positive, you're moving away from your house. Look. Okay, so this is the velocity graph, and as you can see, this is the function, and then it just put it into Desmos, and it gives you the graph. And so between 0 seconds, which is right here when y equals 0, and 5 seconds, which ends right here, you can see that the velocity goes down and then hits a little point right here and then starts going up again. So when it is when the values are below 0 right here, all this right here, that means that you're going towards your house because you have a negative slope. For the original equation, which you can see right here, the green, it's going towards 0. So whenever you're going towards your house or towards 0, you have a negative velocity. And then whenever x equals 0, those are the turning points. And so right here, all these values are positive, so you're going away from your house. Then after about in 1.3 hours, you turn around, and then you start going towards your house, which is all of this. And then about 4 hours, you get turned around again, and you're moving away from your house. So then all this is just moving away from your house. And then in this graph, it just shows the different things that we've done. So this green one, this is the original equation that we were first given. And then this red one is the derivative of that original equation. So that is our velocity equation. And then lastly, this blue one is the derivative of the velocity function. And that's just this blue one right here.
All right, now, how do you find the acceleration?
I just take the derivative of the velocity function. You just take the same rules as before, and it'll look something like this. Alright, so for this, to find the acceleration, you just do the same exact thing that you did for the velocity, when you take the derivative, except you take the derivative of the velocity function instead of the original function. So the velocity function was 3t squared minus 16t plus 16. And for this, you use the same rules. You use the power and the constant rule. So the power rule for this one, and remember the power rule is the derivative of a variable with an exponent equals the exponent times the variable and then that exponent minus 1. So for 3t squared, it will be 3 times 2t minus 16 times 1 t0 plus 16. And like before, the 1 t0 just equals 1, and that just gets, I can just get rid of that because it's just 1 times 16, which is 16. So 3 times 2 is 6t minus 16, and then right here you use the constant rule because this is just an ordinary number, which means it's a constant, which means that when you take the derivative of that, no matter what this number is, it's going to be 0. So our acceleration function is 6t minus 16. And that is, and like I said before, that is the derivative of our variable function. And if you wanted to say, you can also say that is the second derivative of our original function.
What does it look like when you put it all together?
Something like this. So when you put all these graphs together, it'll look something like this, where this green one is the original equation that we had, which is right here, and then this red one, which is the derivative of the original equation. So this red one is our velocity, which is a little parabola, and then the last one, the blue one, this is the derivative of our velocity equation. So this is our acceleration function, which is this blue line right here.
You have been very helpful. I just have one more question for you.
Okay, what's up?
Where are the zeros on each graph, and why are they important?
Okay, so